Well, this is Dr. Joe Trout from the physics program at Stockton University. And this lecture is an introduction to waves. Waves are really important in the study of physics, and waves are used in many forms in engineering and in everyday life. So, for example, here's a device that generates electricity by using ocean waves. So it bobs up and down as the waves move through, and it creates electricity. When people think of waves, most people think of ocean waves. Ocean waves are in general, a combination of two waves, a transverse wave and a longitudinal wave. These waves are also different because the top of the wave is moving faster than the bottom of the wave, and that's why we see them start to crash when they come near the shore. If we look at an idealized wave, what happens is the wave moves through the medium, and the medium is the material that the wave moves through. For instance, if it's a water wave, the medium would be water. And if you look at this gull sitting here, and here's waves that are passing by the gull, what will happen is the seagull will move up and down as the wave moves through, but it won't move left or right. So this is known as a transverse wave. And what we see is that the water pretty much stays where it's in its X position. However, the water will move up and down as the wave moves through it. So what we're saying is that even if you're on the beach, the water that hits you from the wave hasn't come from where the wave originated from. So for instance, that water didn't come from out in the middle of the Atlantic Ocean, right? What happens is the wave moves and the medium stays pretty much where it's at. So as I said, there's two types of waves, transverse waves and longitudinal waves. In a transverse wave, the motion of the wave, in this case to the right, is perpendicular to the motion of the medium. So in this case, the student is holding a spring and making it bounce up and down, and waves are moving to the right. However, the spring is moving up and down. A good example of transverse waves are ripples on a pond or um, waves on a guitar string. Longitudinal waves, in that case, what happens is the wave moves to the right and the medium moves back and forth, left and right. So we say that the medium is moving parallel to the motion of the wave. So in the first case, the transverse wave, the wave moves to the right and the spring moves up and down. For longitudinal wave, the wave once again is moving to the right and the medium moves back and forth, a parallel to the motion. So here explains what happens with the spring. So if we get the spring to compress a little bit, right, that's shown here, what will happen is this compression will move down the spring as time goes on. And here's a new compression started, and it follows the spring once again. So most of us are most used to looking at transverse waves. So we're used to looking at ripples on ponds and things like that. Don't forget, ocean waves are actually a combination of transverse and longitudinal, so we won't talk about that right now. But right now, what we see is here's this wave, and it's moving. Well, the dotted line is when it's at time zero, and then it's moving forwards, right? So what we see is that after 3 seconds, the wave would look like T. And what has happened is this crest, this top part here, has moved over to this position. All right, so here it is now. And 3 seconds ago, it was back here. Okay, so it's moving to the right. And once again, if this was a string or water, the water or the string would be moving up or down. We call the length of one wave the wavelength. So for instance, we can measure the wavelength from crest to crest, or we can measure it from trough to trough. So the highest point is usually called the crest, and the lowest point is called the trough. By the way, when there's no wave moving through, then the equilibrium point, right, is along this axis, and that's where the water or the string would be if there was no wave. If you look here, this is the distance traveled by the wave in the 3 seconds, okay? And what we see is that this is equal to 8 minus 2, which is 6, divided by 3. So it's moving at 2 meters per second. A lot of times we start out by looking at a pulse. So next time you're in a bathtub or there's some water, just take your hand and push the water for a second. And what you'll see is that a pulse of water will move away from you, right? So this pulse, we're going to consider it to be a solid, right? So treat it as a solid, and it's moving to the right. And the position, since the velocity is constant, will just be the velocity times time. So the distance it moves is just the velocity times time. So in lab, we'll be working with the string vibrator, and what will happen is there's this little piece that moves up and down and causes the string to move, okay? And what we see is that as this thing moves up and down, the wave will move down the string. Normally, we represent these waves as sine waves, right? There's only one problem. A sine wave goes between -1 and 1, and it repeats every 2 pi. Okay, so that's what a sine wave looks like. Our wave looks a little bit different, right? So our wave has an amplitude of 0.2 meters, right? And the amplitude is the distance above the equilibrium point. Okay. And here, what we're going to see is that we look at this wave and it's moving down the string. And let's say it's moving at 0.25 meters per second. And let's say we watch it for 0.8 of a second. It'll move 0.2 meters. If we were to plot position versus time instead of position versus x, what we'd see is that if we watch the water, it'll move up and then it'll move back down and then it'll move up. And the time for that to happen once is called the period. So if we plot position versus time, y position versus time, what we see is the time for it to repeat once is called the period, and we use a capital T for the period. We could come up with an equation that will describe this motion. And what we'd actually do is break this up into the force along the string into 2 components, a point that moves in the x direction and one that's perpendicular to it, right? And the actual force is the sum of these 2 forces. These waves can be very destructive. So for instance, if we look at earthquakes, what we see is that whole buildings could be destroyed by these earthquakes. But notice something funny. Notice that some of the houses are completely destroyed. And some of the houses just have their roof torn off, and some of the houses are still intact. And this is because by something called standing waves. So let's take our string vibrator, and if we move it down, and if we let the waves start to move down the string, what we find is that the speed of the wave depends on two things. It depends on the linear density, and that's the mass per length. And it also depends on the tension in the string. So what we find is that the velocity of the wave or the speed of the wave depends on how tight, taut the string is, and the linear density, which is the mass per length of the string. When you think of this, think of a guitar, right? Guitar has those things that called nuts that will tighten the string and increase the tension. And the string and the wave will move faster the more tension there is. It also has different thicknesses of string, right? Which means that they'd have different masses per length. And that's how we get the sound out of it. So let's see what happens at reflections, right? So let's take a wave and we'll send it down. And let's say we have it mounted to a brick wall. And this is called a fixed boundary condition. What'll happen is the wave will reflect, and it'll actually reflect 180 degrees out of phase. So this was a peak, and when it hits the wall, it comes back as a trough. If there's a soft boundary condition, so this is a hard or fixed boundary condition, then the endpoint is free to move. And what will happen is the wave will come down here, the string will move up, it'll move back down, and then the reflection will be in phase. So notice this is a crest, and this is also a crest, right? Or a peak and a peak, right? Where this, the crest, became a trough. So if it hits a fixed boundary condition, it reflects off at 180 degrees. If it hits a free boundary condition, it reflects off in phase or at 0 degrees. This also happens if we move from a thin string to a thick string. By the way, in this thin string, the wave moves quickly. In the thick string, the wave moves slowly. So this is what happens. A wave comes in. Some of it is transmitted, we say, and some of it is reflected. And the total energy here has to be equal to the reflected energy plus the transmitted energy. This is like a fixed or a hard boundary condition. What happens is the wave comes in, it hits this change in medium, right, or this interface, and some of the wave is transmitted and some of it's reflected. And the reflected wave is 180 degrees out of phase with the incident wave. If we have a soft boundary condition, so here we have a thick string or a high density string, and then a thin string or a low density string. Once again, it's moving slower with the thick string and faster with the thin string. So this has more mass per length. This has less mass per length. And what we see is that some of it will get reflected, but it will be in phase with the incident wave. And some of it gets transmitted. It's also in phase. We also need to talk about something called superposition. So let's say if we had two ripples on a pond and they came towards one another, what would happen is they'd make a big giant ripple. And then after they pass through, it would be as if nothing happened. So this shows two things, right? First is interference. What happens is the two waves come and they pass through one another as if nothing ever happened. The second concept here is the concept of superposition. And what we see is that these two waves add algebraically. So for instance, here's a wave it's 1 meter high. And here's, or a ripple. Here's a ripple in a pond, and let's say it's 1 meter high. And here's another ripple, and it's 1 meter high. And they come together, and for an instant, they form a ripple that's 2 meters high. Just the algebraic sum of the two. And then they pass through one another, going back to their 1 meter height. So here shows two waves, a blue wave and a red wave. The blue wave is 1 meter high, and the red wave is 1 meter high. And if we add these two together, we end up with a wave that's 2 meters high. By the way, those two waves were in phase. So notice here's a peak, here's a peak. I get twice the height of the peak. These two waves are out of phase, so they're the exact same wave, only here's a trough and a peak, and they add to 0. Here's a peak and a trough, they add to 0. Here's a trough and a peak, they add to 0. So they add algebraically. And any two waves will add like this. So for instance, here's a wave, and let's look at the red wave. And at this point, it's 8 meters high. And the blue wave is 10 meters high. And the resultant wave, the sum of these two waves, would be 18 meters high. And if we look at this point here, the first wave is 9.5 meters, and the second wave is 9.5 meters. And we add them together, we get 19 meters. Right? So they just add together algebraically. By the way, it doesn't have to be so clean and so simple, right? Here's two waves that'll add together, and we get some crazy looking wave. So for instance, here's the trough and the trough, and we get a peak and a peak, and we get a big peak. And here we add a trough and a high, a positive part of the wave. And what we'll see is this resultant wave that looks like this. Okay, so what we're going to do is send two waves down the medium. And by the way, we'll write these waves when we get in lab as an amplitude times the sine of k, which is 2 pi over the wavelength, and omega, which is 2 pi over the period. And what we'll see is we'll get these waves. And when the waves are completely in phase and overlap, right? And by the way, the red waves moving to the right, the blue waves moving to the left. Sometimes they're both in phase. So the reason in this first picture we don't see a red and a blue wave is because they've overlapped here. And we get twice the height. And here, the red wave starts moving to the right, and the blue wave starts moving to the left, and our resultant wave is smaller. Eventually, the two waves will be out of phase, and the resultant wave becomes 0. And then it continues on. So these types of waves, where we have two waves moving in opposite directions, are known as, the resultant is known as a standing wave. And the reason is because they look like they're standing still. So here's a picture of, this is actually milk in a bowl, and it's being vibrated by a fan. It's sitting on top of a motor. And what you can see is that there's these waves that are here. And these waves are actually standing waves. They look like they're standing still. It's not, if this was a movie, they would still look like they were standing still. So these are called standing waves. And these are the same waves that cause problems with earthquakes. So for example, here's a little closer look. The red wave is moving to the right, and the red wave is moving to the left, and the blue wave is moving to the right. And what we see is if you look at the resultant wave, there's certain points that are always zero. And then this part of the wave seems to oscillate up and down. But really, it's caused by two waves that are moving in opposite directions. So here would be the resultant of these two waves, right? What'll happen is we get these things that never move, and these are called nodes, and we get these points that move at some maximum position, and they're called antinodes. How we can do this in the lab is we'll take a string, and we'll take something called a string vibrator, and we'll hang a weight over this. And mu is the mass per length, and we'll make it a constant, right? So the string doesn't get thicker or thinner or anything like that. And then we'll move this up and down. And what we'll end up with is designs that look like this. Okay, so when we get in lab the first time, what we'll do is set up these standing waves and try to figure out what's going on. In this case, there's a node here and a node here, and then an antinode between them. If we increase the frequency, we'll get a node here, a node in the center, and another one here. And if we increase the frequency again, we'll get 4 nodes. And if we increase the frequency again, we can get 5 nodes, right? And we say that these endpoints are called boundary conditions. And in this case, they're fixed. That means that the string can't move at these points. Excuse me. So we can get things that look like this, but we can't get things that look like this. We can't get standing waves that have an antinodes on the end. And what we're going to do and get into the lab is we'll look at this condition and we'll start to measure these wavelengths and try to figure out what's going on. Right, so that was a quick introduction to waves. And the most important thing is that we talked about was that we have 2 types of wave, transverse wave and longitudinal wave. A good example of a transverse wave is a ripple on a pond. A good example of a longitudinal wave is a sound wave. And what we're going to do is go into lab and create standing waves and see how they work. So this was a brief introduction to waves. Thank you.